Welcome to the short video on our ICASSP paper titled Implementing Continuous Head-Related Transfer Function Measurement in Near Field. I'm Ee-Leng, and I'll be your presenter for this video.
With the increasing adoption of virtual, augmented, and mixed reality technology, we are seeing a significant shift in the way we interact with the world around us. Head-Related Transfer Function, or HRTF, is an essential component to creating an immersive listening experience over headphones for VR and AR applications. Since many of the interaction in this application will take place in the near field, an efficient approach to obtain or measure near-field HRTF will be desirable. Near-field HRTF are highly individualized and depend on directions and distances. Hence, a significant number of HRTF measurements at different distances in the near field will be needed. Using conventional static stop and go measurement methods to acquire this HRTF will be time-consuming and tedious for human listeners. In this paper, we propose a continuous measurement system that efficiently captures near-field HRTF in the horizontal plane. Before I discuss the proposed system, let's take a look at three key approaches to generate near-field HRTF. The first category of approaches involves synthesizing near-field HRTF from far-field HRTFs. One common technique in this category applies the distance variation function on far-field HRTF to synthesize near-field HRTF. This function describes the changes of a HRTF corresponding to the distance of the sound source. These analytical solutions are obtained from a rigid sphere model, which is close to a first-order approximation of the human head. However, high-frequency parallax effects are usually omitted in this approximation since there are no pinna in the rigid sphere model. The second category of approaches involves synthesizing near-field HRTF using numerical methods, which includes BEM, FEM, and FDTD. However, these approaches are of high computation cost and employs non-trivial acquisition processes to obtain the listener's geometry. The proposed system falls into the third category of approaches, which performs a HRTF measurement in the near field. There are two main challenges in measuring near-field HRTF. At close distances, reflection and scattering between the sound source and the listener might occur. This problem becomes more serious for a multi-sound source system due to multiple reflection and scattering among sound sources. You and his colleagues have numerically analyzed the influences of the reflection and scattering on near-field HRTF with respect to the sound source size. Based on their results, we have selected a sound source of 11 cm in diameter. Higher measurement errors are likely to occur even with small head movement. A head tracker is employed to pause the HRTF measurements if a large head movement is detected. Let's take a closer look at the proposed measurement system. For each set of measurement in the horizontal plane, the head tracker is calibrated at 0 degrees. The HRTF measurement starts with the sound source emitting white Gaussian noise as the excitation signal, and the listener is facing 0 degrees. The listener is then rotated and the measurement process is completed when the listener is back at 0 degrees. The head-related impulse response is estimated using adaptive filtering. The normalized least mean square method is selected for implementation due to its high performance and ease of implementation. Any movement of the listener during the HRTF measurement will affect the consistency and the accuracy of the measurement. To evaluate the consistency and the robustness of the proposed system, we analyze the HRTF measurements of heads and human listener using spectral differences and interaural time differences. 8 sets of measurements in the horizontal plane were obtained with heads, and the first set of measurement is taken as the reference. 7 sets of SD profile were then obtained and plotted in this slide. We can make several observations from this plot. Low and high SD values are generally observed near the ipsilateral ear and near the contralateral ears respectively. The higher SD values are primarily caused by head shadowing effect and the high complexity of the contralateral HRTF characterizing the multi-path wave scattering across the head. Let's have a closer look at one of the SD profiles. We can better align SD with human perception by summing up SD values across 40 warp equivalent rectangular bandwidth bands. And this lower plot shows the distribution of errors across the 40 ERB bands. The differences between the HRTFs and the reference HRTF mostly lies between the 21st and the 39 ERB bands at azimuth between -130 degrees and -95 degrees, and 32nd and onwards ERB bands at azimuth between -90 degrees and -60 degrees. It is interesting to note that there is a significant reduction of SD value at azimuth of -80 degrees and -85 degrees. Here we have the HRTFs at azimuth between -85 degrees and -95 degrees. As compared to the HRTF measured at -95 degrees, The HRTFs measured at -85 degrees and -90 degrees exhibit reduced complexity, which in turn leads to lower SD values. Comparing the SD profiles for human listeners with those obtained with heads, similar trends for the ST profiles are observed. Sound localization is based on the difference of sound at the ears. A comparison of the ITDs measured from the human listeners and heads is shown here. It is clear that ITDs measured from the human listeners and heads are very similar, and there is very little deviation of ITDs across different sets of measurements. To conclude this presentation, I would like to highlight 3 points in this video presentation. The proposed system captures near-field HRTF in the horizontal plane in 45 seconds. Our experiments confirm that low and high SD values are found at measurements near the ipsilateral and contralateral ears respectively. Our experiment shows that near-field HRTF obtained using our system exhibits consistency across measurements.
We'll now come to the end of the presentation. We will be presenting our poster on the 6th of June at 10:50 EEST, and we will be delighted to share more of our research finding at the poster session. We look forward to seeing you there. Thank you.